want to hit. I've got it right here. So we are going to go over problem number 20 before we get started. So problem number 20, oops, if I can, is the set of all real numbers x such that x is not equal to 4. And we want to graph this here. Now, so the first part tells us it's the set of all real numbers, yes? So it's everything except for what? 4. So we know that x cannot be 4, yes?
Oh, really?
Yep, we're saying it's everything except for 4. Mm-hmm. Any other questions? Or any other ones that y'all want to look at?
And on, what is it, 7 through
14?
Yeah, you were just supposed to do like the number, comma, number, right?
Yes.
Okay.
So like on number 7, because it says 3 is less than x is less than 9. So we would have the 3, 9, because those are our two endpoints. And we would use parentheses around both because neither one of those is included.
Okay. Mm-hmm. And I didn't realize I had to do that at first, so I did graph it, but I did also put the answer right beside it.
That's fine. Mm-hmm. And again, if you guys have any questions, we will go over 2 or 3 at the start, and then we'll go on with the lesson. Also, if you have questions that you just absolutely have to know, email them to me, because I can answer those pretty quickly as well. Now, what we're looking at today is parent functions. Now, I will say this. The AC just kicked on, which is nice. So, sorry, that distracted my train of thought. What we're looking at today is parent functions and their transformations. Tomorrow will also be transformations. We'll go a little bit deeper into it. But as you've noticed, with most of this chapter, we're going to be jumping around. Because, I mean, from this, so we were talking about yesterday sets and set notations and inequalities. Now we're talking about parent functions. Tomorrow we're going to talk about transformations. We're going to end up talking about matrices. It's a lot of different stuff in this first chapter. And again, I think I said this the other day, this is the only chapter that's going to jump around this bad. All the other chapters are going to stick to a key concept and stay with that through the chapter. So, what we're talking about today is parent functions and their transformations. So these here are 4 parent functions. There are others that we could have, but these are the 4 main ones that we're going to look at here. The first one is a constant function. So the general rule f of x equals 1. This is the main parent function. It's a line. Just a flat line, doesn't increase, doesn't decrease. It's a constant function. It stays constant across the graph. The domain is all real numbers, and the range is just whatever it equals. So y equals 1. If it said that y equals 2, the domain would still be all real numbers, and the range is just 2. Y equals 2. So we have our constant function, linear function. F of x equals x, or we would say y is equal to x. It's the equation of a line, our basic equation of a line. And we have the absolute value, or I'll write it above it this time. Y is equal to absolute value of x. And we have the same thing for the quadratic, y equals x squared. Now, the reason they call these the parent functions is because these are the most basic versions of these 4 here. Now, they use the parent, or they call these parent functions because every other function is going to look like them. There's going to be some changes to it, but all the other functions of these types will look similar to them. Now, this may be good or may be bad depending on how you think of it, but for pretty much all of us in here, we look or resemble like one of our parents, yes? And again, you can take that however you want, but again, we do end up showing some resemblance to one or the other or a combination of the two. That's why they're calling these the parent functions, because any other linear function that we have will resemble this one here. Any other absolute value, if you look, because y'all dealt with absolute value. So y'all dealt with absolute value in Algebra 1, yes? Because it was a V shape, and we didn't deal just with the absolute value of x, because we had the absolute value of x plus 3, and it moved around, it looked different. But whenever you looked at the graph, it was still always a V shape. So even though we can change it and move it, it still remains and has that value of this parent function. And the same thing is true with quadratics, because any function that is a quadratic will still retain this U shape. It may not look exactly like this, but it will still have that U-shaped quality. And there's different transformations that we can do or apply to these here. Okay? Now, where are different transformation types that we will have? They have vertical and horizontal stretches, because we can stretch it. We can either make it increase faster or increase slower. Or we can stretch it so that it's increasing faster along the x or slower along the x, or increase it faster along the y or slower along the y. We can move it up, we can move it down, we can move it left, we can move it right. So we can move it in all these different directions. Now, for the most part, we won't talk too much about, you don't have to write this down, horizontal stretch slash shrink. And it's not that it's because it's too difficult, it's an easy concept, but it's something we have to keep track of. Does that make sense? It's not an overly difficult process, but it's just something we have to keep track of to make sure we do it right. Because whenever we talk about a horizontal shrink in the function, we call it b is really 1 over whatever that value is. It flips. So if in the function it said horizontal shrink, this here, for x, the actual amount that it shrinks or stretches is actually 1/4. So it's a shrink of 1/4. Or now it's a stretch of 4, because we have to flip it. So that's one of the weird things with horizontal stretch and shrink. But we don't talk too much about yet. Now for these first few here, we're going to identify the family and kind of give not full detailed terms, because by the time we finish this section of notes, we will give more detailed terms and definitions of how it's being moved. But for now, we'll deal in more of kind of general sense. So the first thing we want to do is identify which family this function belongs to. Because we have 4, it's either going to be constant, linear, absolute value, or quadratic. Which one do we think this is? Which one of the 4 do we think this is going to be? Absolute value. What gives it away? It's a V. So it's an absolute value kind of function because it has a V. They did give us the function here, which does have the absolute value of x, but the V shape is really what gives this away. Now again, I said we're not going to deal too much with graphing. I believe I said that in here because I don't see its overall importance with the amount of technology that we have. So it's saying to compare the graph of f to the graph of its parent function. Now the parent function is going to start here and go this direction. Okay. All right. I don't want you back here. Yeah, it's wanting to grab a hold of it So this here would be the parent function. Yes, sir. You might have gone in the other door. I think they're checking on the AC.
Well, he was standing there.
Okay. So we have this here. This is the parent function, and we want to see how does it relate or kind of compare to the graph that we had to begin with. Now, looking at this here, what's one thing that we can say that the one that we drew here, that I drew in, compared to the original one? What's something that's changed?
Wider.
So it's wider, or, because we're going the other direction, so it wouldn't be wider, it would be narrower. Because we're going from black to blue.
Oh, I see.
Yeah, because the black one is the parent. So we're wanting to compare the graph of F, the blue one, to the graph of its parent. So it's narrower, yes? Or in more, not completely scientific terms, it's increasing faster. Because when we think about it along the y-axis, the one in black is increasing slower than the one in blue, yes? Because when we think about its movement, it is going up faster. So we can say that it's increasing faster. But there is one other difference. Where's it starting? Where's its lowest point? 0 for the one in black, yes? What about the other one? 1. So what did it do? It's up 1. Because really, even if I moved both of these up 1, we can see that the blue one is increasing at a faster rate. Now we'll get into it, but that increasing that faster rate is actually called a vertical stretch, because we're stretching it vertically. It's increasing faster. But that's it. So really, once we get into more technical terms, we'll define that increase by a vertical stretch, and we'll know what the factor is. And it is up 1. So what would the parent function for this one be? Linear. It's a linear function. Equation of a line. Let's do arrows both sides. So this here is probably supposed to, I'm going to get to actually drawing this, but that there is the parent function. The linear line, the basic f of x equals x, because the linear function's parent is f of x equals x. So now we need to see how it relates to this here. Well, it's definitely been moved up, yes? Because it's not at 0 anymore. It's now crossing this axis at 6. So it's been moved up 6. Okay. Oh. There we go. So we do have it here, yes? But it's not going up anymore, is it?
No.
Down, which we would say has been reflected. Try it again. And we'll get more specific details about how it's reflected, but it is being reflected because it's not going up anymore, it's going down. And really we would say across the x-axis. There it is. Flip. Up, down. Okay. So we got that, yes? So now it looks more like it's supposed to. It's going down, yes? So the parent function is y equals x. So that's our function. So, and it's pretty much, this is just doing it a while, but tables, so 1, 1. So when x is 1, y is, or I'm just plugging in values 1 to 1 for y equals x. Now, once we get through this section here, or this 1.2, once we get past these, it'll start making sense how we can tell this. We can tell what these are without the graph of the parent. We know what's going to happen, and it'll make sense here in a minute. But for now, we kind of need this to be able to see what's happening. Now, the last part is, well, as we can see here, this line is not increasing or going as fast as this other one, yes? So the other one is another stretch where it's increasing faster. Or we can say it's increasing. Now, even though it's going down, we consider it a stretch or an increase here. Questions on this here? Okay. We're going to look at the last one here. Mainly, what is the parent function for this one? Quadratic. How do we know it's a quadratic? It's a U shape. Now, yep. It's quadratic. Now, there is a stretch here. There's a horizontal or vertical stretch and a translation to the right. But before we get too bogged down in this, let's actually start looking at more of the detailed versions of these transformations. Now, the first transformation we're going to talk about is a translation. It's a transformation that shifts the graph horizontally or vertically, but does not change its shape, size, or orientation. Does not change shape, size, or orientation. So, for a linear function, y equals x is our linear function. For our you know what? Probably not going to like this, but absolute value is y equals a. We have these here. Now, these here are the general form of all of these functions. Now, when we talk about a translation up and down, we're talking about the value of h. No, sorry, k. Value of k. Up and down. Is going to be our k. It's going to be up if k is positive, and it's going to be down if k is negative. So the function moves up if k is positive, and down if k is negative. Bless you. The left and right will be the value of h. Now this one here is a little bit funny because, again, if h is positive, it's going to move to the right. If h is negative, it's going to move to the left. Now, if you look in the function, the two places where h appears, what's the sign in front of it? So h, negative and negative, yes? So if h is positive in this function, it's going to look what? Negative, because if I subtract a positive number, it's going to look negative, yes? So for this here is left and right. So if it, say if I plug a negative in here, a negative and a negative make a, so inside the left and right, if it's going left, it's going to look positive, but if it's going right, it's going to look. So whenever we're inside the parentheses or absolute values, it's the opposite direction of what we think. Inside is left and right, outside is up and down. So again, we're not too worried about graphing it. But looking at this first function here, g of x equals x minus 4, which is the parent function? Linear. Because again, we do have an x, but its exponent is 1. We don't have any squares. So this would be a linear function. Now looking at this here, so we have x minus 4, yes? Now in the general case, I'll write it up here. Y equals ax plus k. What is the negative 4 in the place of? What place would it take? K. Which direction does k move? It moves up or down. So what is the value of k? Negative 4, yes? So it's going to move 4 units. Which direction? When we describe its movement, it is down 4. Because now that we can start seeing it now up, down, left, right, we can look at that and see what it's going to do. Mm-hmm. Yes. So if it had been plus 4, it would have been up 4. So which one is this parent? Yep. Absolute value. Because we have the absolute value bars. Now, the general function for this here, y equals a absolute value of x minus h plus k. Is this function moving up or down? No, because for it to move up or down, we need something added outside of the absolute values. We don't have it. We don't have anything subtracted. The only thing that's different is the plus 1 inside, yes? Which matches up to the minus h, yes? So how far is it moving, left or right? 1. Now, is it moving to the right or to the left? Almost. Yes. Now, yes, it is positive, yes? But what's it over here in the function? Negative. So what we can really think of this as y equals the absolute value of x minus, because again, in the general function it's minus, it's not plus. But in order for this to work, the 1 is actually negative, because the negative and negative would give us our positive. So that's one way we can think about it. The other is whenever we're inside absolute values or parentheses, it's the opposite of what we think. It's the opposite of what we think. So since it's plus, we're actually moving to the left. If it's minus, we're moving to the right. And as I already explained with horizontal stretch and shrink, because when we'll get to it, normally with a stretch, we're talking about a whole number. We're talking about a fraction, we're talking about a shrink. As we already saw with horizontal stretch and shrink, that occurs inside the parentheses, and it's flipping. We had to flip it. It's the opposite of what we think. Questions on this here? All right. The next transformation we have is a reflection. I'm going to abbreviate two of these just so it's easier for us to look at. Or not easier to look at, but just to write. So when we talk about a reflection across the x-axis, A is negative. If the number where A is negative, it's a reflection across the x-axis. So if the number in front of the parentheses is negative, it's a reflection across the x-axis. If it's in front of the absolute values where the number is negative, it's a reflection across the x-axis. For linear, it's just going to be a reflection across the x-axis. Well, we have two axes, so there's going to be a reflection across the y. And that's when x is, well, when the number in front of x is negative. Then it's a reflection across the y. And that's mainly talking about absolute value and quadratic when we have those parentheses. Okay? So when the number in front of those, inside the parentheses, when that number in front of x is negative, we're reflecting it across the y-axis. So for absolute value, when it's in here or in here, it's a reflection across the y-axis. Now, linear, it's kind of back and forth because x and y is not going to make too big of a difference just because of how the shape of the graph is made. But for the most part, when we talk about this here, we'll talk about the linear as a reflection across the x-axis. Questions on this here so far? So again, we're not graphing, but this one's parent function would be what? Quadratic. Because the main thing that it does have is the x squared, yes? Well, the only one of these that has a square is the quadratic function. That's what makes it a quadratic. Now we do see that there's nothing being added or subtracted to it in parentheses or out, yes? So that means it's not moving up, it's not moving down, it's not moving left, it's not moving right. It's not moving any of those directions. But we do have a negative, yes? Is it inside parentheses? Is it outside the parentheses? Mm-hmm. If it's inside parentheses, it's reflected across the y. So if it's outside the parentheses, it's going to be what? Reflected across the x-axis. Because again, the negative, when it's a, well, yeah, describe the transformation. Because that's what we're doing, we're just describing the transformation. Now, I'm not going to make y'all graph it because that's the other part that it really wants, but we're not concerned with the graph. Questions on this here? So what is this one's parent function? Linear. We don't have any exponents. Yep. I'll give you another second. Okay. Now we need to describe the transformation, yes? So we do have a negative. So that means we're talking about some type of reflection. So it's reflected across what? This one here, we could consider it the y. but we're mainly going to call it the x-axis. Because again, the y-axis, we would really need parentheses or absolute values. It needs to be on the inside. You're good? Because for this one here, linear is really almost both. Could be one or the other, you can pick. But that's just because it works funky with linear functions. But that's it. All right. So what's the parent function for this one here? Linear. Linear. And how was this one moved? Are there any negatives in front of the x or parentheses? No. So is it going to be reflected? No. Okay. We do have the +3, yes? Is that going to be left, right, up, or down? Up. It's going to be up and down because it's not inside parentheses or absolute values. So we're talking about up or down. And exactly, it is up 3. Because if it's outside parentheses or absolute values, it's exactly what we see or exactly what we think. Since it's positive, it is up, and it is up 3. That's it. Because we would need the negative. How about this one here? Quadratic. Now, what's its transformation? So is there a negative attached to the x or outside the parentheses? No. It is left or right because left and right's inside parentheses. So it's going to either go left or right 2, yes? But with left and right, is it exactly what we think it is? No. Because inside parentheses, it's always the opposite. So this here would be, yep, you were right. It is right too. Yep. And a lot of that's what's going to happen here. Because inside parentheses are absolute values. It's the opposite direction of what we think. Because again, the general function for the quadratic is x minus h inside. So we have x minus h. So the h value is actually 2, positive 2. So it's moving to the right. Or we can think of it, since it's minus inside the parentheses, it's not going left, it's going to the right. Questions on this here? This one is absolute value. Do we have anything being added or subtracted inside or outside the parentheses? But there's a negative, yes? And negatives deal with what kind of movement? Not up or down. I didn't actually write it. Reflection. Yep. Because if it's attached to something as a negative, changing the sign, then we're talking about reflection. Because we're not actually talking about adding or subtracting something. This is going to be a reflection. Now we need to figure out which axis. If it's, since here it's outside the parentheses, or absolute value, outside the absolute value, so which one would it be? Almost x. Outside is x, inside is y. So this one here is reflected across the x-axis. Are you ready for the next one? So the last main one we're going to talk about is vertical stretch and shrink. Vertical stretch and shrink is going to be mainly revolving around A. Okay? So the general functions, so you can rewrite them back out. I think most of y'all are referring back to the first ones you wrote down, yes? these three here. When we talk about vertical stretch and shrink, we're talking about A. If A is greater than 1, it is a vertical stretch. If A is greater than 0 but less than 1, it is a vertical shrink. And we call it a stretch or shrink by whatever that number is. So if it's greater than 1, it's a stretch. If it's less than 1, but greater than 0, it's a shrink. But notice with this here, is A in either case negative? No, because if A, this value is negative, it's not talking about vertical stretch or shrink. It's talking about a reflection across the x-axis. You all see the distinction there? The negative is not attached to this here, it's attached to the reflection. So, if we look at this here, so we can mainly just talk about the transformation. So we have a 2 being multiplied out in front of the absolute value, yes? That's taking place of A. That's where A is sitting, yes? So this here would be a stretch or shrink. And it'd be vertical, what? Vertical, because is the A value greater than 1 or between 0 and 1? Greater than 1. 2 is greater than 1, yes? So this would be a vertical stretch of, what's the value of A? So it's a vertical stretch of 2, because it's telling us how much the stretch is occurring. And that's it. Questions on this here? So this one here, we have 1/2 in the front, yes? So this would be what? Yes, it'd be a vertical shrink of what? And that's it. Because the 1/2 is taking the place of A. A deals with vertical stretch or shrink. Since 1/2 is in front of the x squared, it would be a vertical shrink of 1/2. Yep, because it's between 0 and 1, it's a stretch, or sorry, shrink. Greater than 1 is a stretch. How about this one here? Yes, vertical. Yes.
Basically, we just have to look at the one beside the x and see how big it is.
Yep. Would tell us stretch or shrink. Right, because if it had said negative 3x squared across the x-axis and a vertical stretch of 3. So any questions on this here? Because I think y'all about got these down, yes? So this one here, we can talk through this one. This one here would be what? A vertical shrink of, because it's less than 1. This here would be vertical stretch of. This one here is a little tricky. Because what is it? 3, which is what? 1.5. So it's greater than 1. So it'd be a vertical stretch of 3/2, or 1.5. So that's, just because it's a fraction doesn't mean it's automatically a shrink. And I think that was the last one on your note sheet, yes? But I want to look at this one here. So look at this one here with me before we wrap up. If you notice this here, there's more than one thing going on, yes? So if we go left to right, looking at this here, the first thing we have is that negative out in front of the absolute value, yes? Well, according to us, or what we've done, that would be a reflection. So this isn't in your notes.
Okay.
The negative out front would be a reflection, yes? Across what? Across the x-axis, because it's outside of those parentheses. Outside the absolute value would be a reflection across the x, yes? But that's not all we have. We have plus 5 inside, which would be left 5, because it's the opposite of what we think. But we still have one more. We have the minus 3 outside, which would be almost. Yeah. So all the ones that we did today, we can use them together in one. We don't just have to have one function. But the placement of them does not change. Because if there's a negative outside, it's a reflection across the x-axis. What the numbers added or subtracted inside absolute value parentheses moves it left or right. And outside added or subtracted moves it up or, and that's it. So we're looking at one at a time. Questions on this here? Well, page 14 really doesn't matter, because y'all have page 14. So if you want to circle the ones. So 3 through 6, 9 through 15 odd, 19 through 25 odd, 27, 28, and 31. I will post this in Google Classroom. But again, one of the biggest things, don't graph. Do not graph. I'm not asking you to graph any of these here, okay?